Can you all hear me in the back? Yeah? Okay. If somebody can't hear me, maybe they should move forward a little bit. Hi, everyone. My name is Kirill Solovey. I'm a postdoc in Professor Pavone's group, and I'm substituting him today. And today we're going to talk about a very fundamental problem in robotics, how to plan motions for robots, collision-free motions. Okay, so we're going to spend this lecture and the next one talking about robot motion planning. Okay, so what is robot motion planning? Here we have a very silly illustration for that. We're given some representation of our robot. In this case, it's a free-link robot, but it can be a turtle bot, a spacecraft, autonomous car, etc. We're given some representation of the environment of the robot. In this case, we have those gray obstacles. We're given a start configuration and a target configuration. And our goal in motion planning is to compute a trajectory or a path for the robot that moves it from the start configuration to the target configuration while avoiding collisions with obstacles. It may also be collisions with itself if we have this type of robot. And we may also need to satisfy different kinematic or dynamical constraints that are induced by the robotic system that with which we're working. Okay, so this is the robot motion planning problem. Any questions so far? Okay. So, of course, we're talking about robot motion planning. And techniques for motion planning are used extensively in robotics to plan paths for humanoid robots, plan paths for steerable for cars, for autonomous, for spacecraft, etc. But it's worth mentioning that motion planning is not only applicable to robotics. For instance, one of the main motivations why people or people in the academia started to look into motion planning was actually solving puzzles. Okay, so what is the analogy between those puzzles and robotics? Are you all familiar with this puzzle? It's called the 15 puzzle. Here the goal is to move those little bricks around until we get a straight number of 1, 2, 3, etc. Okay, so the analogy here is this can be actually viewed as a robotic system. It has a specific constraints. We're given a specific initial configuration and a target configuration, and we want to find a motion that satisfies our constraints. Okay? Techniques for motion planning are also used not only to design paths for steerable needles that are used in surgeries, but also to design the steerable needles themselves. And in recent years, techniques for motion planning are also applied to understand how proteins move and dock with each other and interact with other proteins. So what is the analogy? Why we can think about those proteins as robots? Because they have hundreds of links, and those links revolve each around the other. And we can basically think about this protein as a very complex robot. So techniques for robot motion planning are actually applied to study how proteins move in the world. So people have started to look into motion planning already in the 1970s. Back then, they mostly had heuristics, meaning algorithms that sometimes work, sometimes do not work, and it's not clear why they don't work. In the late 80s, people, especially from the field of computer science, started to design a combinatorial algorithm to which we reach later on in this lecture today. So those complete combinatorial algorithms have already theoretical guarantees, meaning that they are guaranteed to find a solution if one exists, or to declare that no solution exists otherwise. In recent years, sampling-based methods have become increasingly popular. Those techniques, which we'll cover in the next lecture, are basically randomized versions that apply randomized sampling approaches over the combinatorial solutions that I just mentioned. And nowadays, sampling-based algorithms are used for various complex problems in motion planning, including differential constraints on the robotic systems, planning under uncertainty, and other very interesting and very practical aspects. Okay. So today we will cover grid-based methods for motion planning, which are the basis for all the next approaches that we will see later on. And we will eventually reach geometric algorithms, which are examples of those complete combinatorial solutions that I just mentioned. And in the next lecture, we will cover sampling-based algorithms. OK, so what is the setup? What are the ingredients of the problem? So we're always given some representation of the workspace in which the robot operates. In this example, it's a two-dimensional workspace. Okay, but it can also be a three-dimensional workspace like this class. By the way, how would we represent the workspace in such a case? What is the typical way we would represent two-dimensional objects? It was a question? Yeah? Sorry? A set of vertices. So you mean like a cloud point? Or OK, this is one way to do it. Usually the problem is that the points don't really capture how the points are related to one to another if we don't have any edges between them. So the typical way to represent those structures is by polygons. Okay, a polygon is simply a set of vertices that are connected by straight line edges one to another. Okay? So the input for this problem will be a set of polygons that represent the workspace of the environment. Okay, and of course we can generalize this polygon to 3 dimensions. We will have a polyhedron, etc. So this is one of the inputs. We're also given a representation of the robot. In this simple example, our robot is again a polygon, the yellow shape. Okay? We're given also as an input an initial placement for the robot and the goal placement for the robot. And the problem is to find a motion that moves our yellow robot from initial to goal position while avoiding collisions with obstacles. Okay? Is that clear so far? Okay, so this is a very basic example. Most of the lecture today will talk about this simplified version, although I will also cover some more realistic cases. Okay. So we will cover 3 approaches. And the first approach is called grid-based planning. By the way, how many of you have studied A-star algorithms or have some background in computer science? OK, that's good. But don't worry, for the rest of you, we will cover all those things in this lecture. So what are grid-based approaches? Grid-based approaches essentially ignore or discretize the geometry of the environment into a grid representation of a graph. Okay? Meaning that in the example we had earlier, we may take a fine grid, overlay it on over the workspace that we have or over the problem, and we mark each cell of those grids by a free grid cell or a forbidden grid cell. Okay? Like in this example. So here we have forbidden grid cells, and the white ones and the green and the red represent free cells. Okay? We can move the robot from one cell to the adjacent cell, okay? Assuming that they are connected, and those 2 cells are free. Okay? So this is a discretized version of the problem. And let me be more formal here. We can describe our new problem, the discretized version of the problem, as a graph G, consisting of the vertices V and the edges E, where every vertex represents a free cell, and an edge represents connections between adjacent cells. Okay? Okay, so now I described this problem in this simplified version. What is the graph analogy for the motion planning problem that we had earlier? Earlier we had some physical entity that needed to move in an obstacle-free region of the problem. What would be the corresponding problem on the graph? We're given a start vertex and a target vertex. And what do we need to find? A sequence of what?
Viable cell
Sorry?
Possible cell sequence.
Yes, of free cells, a sequence of free cells that would allow us to move from the initial cell to the target cell. Okay? So just to clarify, from a practical standpoint, given a solution for the discretized problem, how do I convert it into a solution for the robotic system that I'm working on? Yes? Interpolation, but let's start with the basics. What every cell represents, what a given cell represents. And we can have many different answers for that. So for instance, we can think about each cell as representing one specific point in space for the robot. Okay? An edge between two adjacent cells represents what? A basic motion that moves the robot from the center of one cell to the center of the adjacent cell. Okay? And a path that consists entirely of free cells in the graph represents a free path for our robot. Okay? So we took the continuous problem that may be very, very difficult and discretize it into a very simple graph representation. Okay? Any questions so far? Is it too slow? Too fast? No? Okay. I'm just not hearing any reaction, so. Okay. So the first approach that we take is first take the problem, the original problem, discretize it into a graph, and then find a solution on the discrete graph and convert it back into a solution for the continuous problem. Now is the question, how do we find efficiently a solution on the discrete graph? Okay? And we will see a number of approaches. Here we have an illustration of one of the approaches. We're starting in a specific configuration of the discretized graph, and we want to reach this target vertex. So what most of the search algorithms would do for a graph is little by little explore a larger and larger area around the start vertex. Okay? Those algorithms are called in general label correcting algorithms. Okay, so let's just see how it works in general. So those algorithms have a very similar structure in the sense that they all maintain some sort of a priority queue or a frontier of the vertices, where we keep the vertices that we have seen so far. So you can think that we start, what is the first vertex that we will put in this queue? The start vertex, okay? In every iteration of the algorithm, we will extract the next vertex from this queue. We will ask, what are the neighbors of this vertex? Okay? Then, in case that we found a new path that leads to one of the new neighbors that we just unraveled, in that case, we update update the cost or the parent of the vertex in the discrete graph. Okay? And when do we stop? So we apply this algorithm for many iterations until we eventually reach a vertex that is in the goal region. Okay? So once again, the basics are, in every step of the algorithm, we extract a new node from the frontier or the queue of the graph. Okay? How do we know what are the neighbors in the graph of a given vertex? We can just look down, up, or left or right. Okay? We only need to store 4, let's say, pointers for the neighbors of a given vertex. Okay? I didn't talk too much about the cost. We will reach the cost soon. But let's just think for now that we only want to find a path that is free or collision-free for a robot. So given a vertex that we extracted from the priority queue, we look at all the neighbors of the vertex. Okay? If one of those vertices is the goal vertex, it means that we found a solution. Okay? How can we retrieve the solution that we found? So we reached a particular vertex, and for every vertex, we also maintain what was its ancestor in the graph. Okay? And once we reach the target vertex, we just have to ask this specific vertex, what is your father in the graph? We get one step backwards. Then we get a new vertex. We ask, what is your father in the graph? And that way, we retract our route until we reach the start vertex. Okay? Any questions so far? Okay, let me just mention that we don't have too much time to go into all the details about those algorithms. We will get into more details when we will talk about the A-star algorithm, which is for your applications, you can think about it as the best algorithm of all those search algorithms, and you will find in the end of the slides a few more slides that explain more in detail the A-star algorithm. Okay, so until now we just focused on finding a path, getting our robot from the start to goal. Okay? Usually we're also interested in finding a good solution in terms of either path length, the amount of energy exerted by the robot, or the safety for the robot. Okay? How can we retrieve good paths using those graph algorithms? Okay, so what do we do? For every vertex that we have seen so far, we maintain its cost. Okay? C of Q is the cost to come for this specific vertex, which means the cost of the best path that we found so far from the start to the vertex. Okay? Now that we reached a new neighbor of our vertex Q, we are checking if the new path that we unraveled for Q prime is better than the path or the cost of the path that we have previously stored for this vertex. If this is the case, what should we do? It means that we found, sorry, yeah?
Just update it with the one that you have that's better.
Right, because it means that we found a better route to reach this vertex than we had stored for it earlier. Okay, how do we see that? The cost of reaching to Q prime from Q is better than the cost that we previously stored to reaching Q prime from a different path. So just to clarify what this means, this is the cost to come of the father of the vertex, Q, plus the cost of traversing the edge from Q to Q prime. Okay? In that case, it means that we found a better route to Q prime. So what would we need to do now? we need to update the new cost that we found. And we also need to update in the data structure that Q prime, the father of the Q prime on the shortest route is Q. Okay? We make this update. We add the corresponding vertices to the priority queue. Okay? We finished one iteration. And then what do we do in the next iteration? Exactly the same thing. Okay? But how do we guarantee that we will reach the target vertex by the shortest route possible? So there are many options how we can do that. But one of the best approaches to find the shortest route is called Dijkstra, is basically extracting from the priority queue vertices according to what law? According to their cost to come. Okay? What is the rationale behind that? That the shortest vertices, the vertices that we have seen so far and the route to them is the shortest, may help to uncover other routes that are short as well, and we will reach the target vertex. Okay? Yeah?
What does your seed function look like for that order case?
Mm-hmm.
Is it just like there's uniform cost everywhere?
Yes, in that case, because it's a grid, let's say every edge has the same weight. So it's basically just the sum of all weights along the shortest path. But this can be actually a more complex function. For instance, you can put here the amount of energy required to traverse a specific edge. And if you have a non-trivial robotic system, then it might be that one edge is more costly than the other. You may also have a grid that is non-uniform, as we have here in this case. Okay? So it was a good question. Thank you. Any more questions so far? Okay. So here we have a few methods how to extract the best neighbor or the next vertex that we will need to expand in order to unravel our graph. All those methods have something in common. First of all, they guarantee that we will eventually find the best solution for our problem. Meaning that if we will run any of those three methods, we will eventually reach our goal vertex. And moreover, the path that we will find will be the one that minimizes our cost function. Okay? This is a guarantee that all those algorithms have. But if we will just look carefully at this example here again, it has some, let's say, a disadvantage. The thing is that it continues exploring vertices in a growing radius around the start vertex, and in some sense ignoring the location of the target vertex. Okay? So even if we start here, and our target vertex is here, those algorithms will eventually uncover all the vertices in this neighborhood, even though all those vertices are farther away from the target vertex. Okay? And this just follows from the way that we extract vertices from the priority queue. We always extract the next vertex whose cost is the minimal one, and we haven't visited this vertex yet. Okay? So in that sense, from the perspective of the priority queue, a vertex that is located here and here have the same priority. Okay? How can we bias those search algorithms so that they will look more at vertices that are located in the direction of our target vertex. And by that, explore less areas that are unrelevant for our problem. Okay, what kind of an idea should we use? Okay, let's say that I want to reach the end of this room. Okay, should I go backwards first? I can't go through those seats, but my eventual path will be somewhere in this region. How can we encode this logic into the search algorithm? Yeah?
Initialize costs like for distance between the current cell and where you want to get to?
Right, right. This is a good idea. So we shouldn't only look at the cost that allowed us to reach this specific vertex, but we will also take into account the cost, the approximated cost, to reach the target vertex from the current vertex. But here there is a small catch. We don't actually know how much it would cost us to reach the target vertex, because this is the entire problem that we are trying to solve. But in many cases, we can estimate this quantity quite well. For instance, I can approximate my cost or lower bound my cost of reaching the target by simply Euclidean distance. Okay? This is basically the cost in a case that I don't have any obstacles in my environment. Okay? So how would we encode this into our search algorithm? This is what A-star does. Okay? So this is the previous algorithms, a group of algorithms that we talked about. And you can see that A-star more intelligently uncovers less regions in the graph. And by that, what it minimizes, it doesn't minimize the cost of the solution, because those algorithms are also guaranteed to minimize the cost. But it minimizes something else, which is also important to us. The more edges or vertices that we visit, what would we increase by that? The running time of the algorithm. Okay? So the idea behind the A-star algorithm is to explore less vertices and edges by using a cost heuristic that biases our search towards the goal region. And you can see just from those animations that this algorithm eventually explores a much smaller number of vertices, and by that, it reaches the goal region much faster. Okay? So while previous methods extracted from the priority queue vertices using the following logic, vertices that minimize the cost to go and the cost of reaching the vertex from its previous neighbor. Here we also extract vertices not only by their cost to go, but also by the approximate cost of reaching the target from the current vertex, and this H represents here the heuristic. Okay? We have a heuristic that gives us an upper bound of how much it would cost us to get to the target from the current vertex. Okay? So now we take into consideration not only the cost to come, but also the cost to go. Okay? So the nice way, and this is the A-star algorithm. The A-star algorithm has all the nice properties that the previous algorithm have, meaning that they will eventually find a solution, and this solution will be optimal. But A-star also strives to minimize the number of vertices or edges that we uncover along the way. So just let me emphasize that it doesn't guarantee to uncover the smallest number of vertices or edges, because this is impossible. This really tells us that we know the perfect, we know exactly how the optimal solution for our problem looks like, which is not the case. But it will usually, in practice, lead to much smaller running times than using Dijkstra algorithm, for instance, or BFS. Okay? Yes?
What are some drawbacks of A-star?
There are actually no drawbacks. Yeah, and typically in practice, people tend to use A-star. Of course, A-star has many. A-star was invented, I believe, 40 years ago, and since then we have a lot more improvements over A-star. There is D-star, H-star, any first letter and star that you could imagine. But for your applications, I believe that A-star would be enough. Okay. Okay. So yeah.
Why do you need to underestimate the heuristic function?
Oh. If you are not guaranteeing to underestimate the heuristic function, then your completeness, the completeness of the algorithm might blow up. Meaning that if you don't have this property of underestimating, it is not guaranteed that A-star will find the optimal solution. This is an important point, yeah.
Sir, what does upper represent here?
The upper, so for instance, you may have already some notion of how much, how costly it will be to reach the target position. Let's say you know that you have some upper bound on the cost of the solution to the problem. So if you find a vertex through which the cost will be already larger than this thing, it's not worth exploring. Okay? And another thing, eventually you may already reach the target vertex, but it may be that you will later uncover another target vertex for which the cost is even shorter. Okay? So you may eventually reduce this upper bound as you go along. Okay? Any more questions? Okay. So let me briefly summarize the grid-based approaches, and if I have some more time at the end, I may go into more details about the A-star algorithm. So those graph-based approaches are super simple, but let me just clarify for your question earlier on the heuristic, what happens if our upper bound is not maintained. We omit here a lot of details, okay, including the proofs for the completeness and optimality, okay? We're using those tools here in this course as black boxes, okay? And of course, we can spend a whole course just describing those algorithms in details. Okay. So as you can see, those grid-based algorithms are super simple to use because they essentially ignore all the inherent difficulty that we have in dealing with real robotic systems and dealing with the planning motions in the real world where we have complex environments. Those algorithms are usually quite fast for some problems. But in some cases, they are just not enough. Okay? In what sense? The first thing is that those algorithms are resolution dependent. We decide a priori what should be the resolution of our grid. It may be that the resolution of the grid that we decided on is not fine enough in order to unravel the narrow path or the narrow passage that we have in our problem. Okay? So those techniques are not complete in the sense that they are not guaranteed to find a solution for the original motion planning problem if one exists, in case that the resolution is not correct. Okay? What is then another disadvantage of those techniques? So until now, we just talked about a very simple example. So here we had an example of a two-dimensional problem. Notice that it is not even the problem that I mentioned earlier with the polygon that can translate and rotate in the space. So basically, we ignored other degrees of freedom that the robot has. Now let's think about a problem where we have already 6 degrees of freedom. And we will get to that later. usually we will need to construct our grid in a space that has the same number of degrees of freedom as our robot. Okay? So this is really easy to do when we have a two-dimensional problem. What happens when the dimensions of the problem increase? What increases on the grid? The number of grid cells. This is exponential in the number of degrees of freedom of the system that we have. Another thing, if for our two-dimensional grid, how many neighbors each vertex here has? 4 or 8, really, it really, or 6, depending on the way you decide to draw connections. When you increase the number of dimensions, the number of neighbors that each vertex has increases exponentially in the number of dimensions. Okay? So the complexity of the grids blows up exponentially, and in turn, our algorithm blows up exponentially. Okay? So those methods become less effective as we increase the number of dimensions of the problem. Okay? Okay. So now we're moving on to continuous methods for motion planning. But the nice thing about them is that they will still use in some intelligent way those graph or grid-based approaches that we just talked about. So what is the difference between the continuous problem and the discrete problem that we had earlier? Now our robot is some geometric entity that moves in continuous space. Okay? This space may be very complex. We may have very complex obstacles. They may be movable, etc. But let's stick for now for static obstacles. So now we will talk a little bit about combinatorial techniques for motion planning. What's nice about those algorithms is that they are exact. They are guaranteed to find a solution if one exists. They are not sensitive to the resolution for which you are working. They are actually not assumed to work with a resolution of the problem. Okay? And the way those methods work, they construct a precise representation, geometric representation, of the free space of the problem, which is the set of all collision-free configurations of the robot, and do all the reasoning on this complex structure. Okay? So let me describe a few basic definitions before that. First of all, a robot's configuration is a complete specification of the position of every point of the robot. Okay? A robot's degrees of freedom is the smallest number, d, of coordinates needed to represent its configuration. Okay? So if we have a robot that is basically a polygon that is only allowed to translate in the plane, how many degrees of freedom he has? Just 2, right? If we also allow it to rotate, we already have 3 degrees of freedom. So the configuration, a configuration for such a robot, a polygon that is allowed to translate and rotate, is basically consists of what? Of 3 coordinates, x, y, and theta. Okay? And we can, in this way, describe more complex robots. For instance, if we think about this 4-joint arm, it has already 4 degrees of freedom because we can describe the relative position of every joint with respect to its previous joint. Okay? And if we have a rigid body in 3 dimensions, then this robot already has 6 degrees of freedom. So the point I want to make here is that even though our robots live in a 2-dimensional or 3-dimensional space, they actually induce a more complex geometric space that has the same number of dimensions as the number of degrees of freedom of the robotic system. So what is this geometric space? It is the d-dimensional space C containing all possible configurations of the robot. This space is called the configuration space of the problem. Okay? So again, just to follow my example here, a robot is a polygon that is allowed to translate and rotate in the space. Its configuration space is a three-dimensional space, which is the Euclidean space times the Cartesian product with a circle. Okay? Any questions? Okay, so these are a few basic definitions. We had the configuration space. Having described the configuration space, we are actually interested in a subset of this space, which induces the set of all collision-free configurations for our problem. This is the free space of the problem. Okay, so here we have a very simple example. A disk robot, again, allowed just to translate in the space and has this obstacle in the environment. What is the configuration space of the problem? It is the two-dimensional Euclidean plane. What is the free space of the problem? How would look all the configurations in which the robot is not in collision with the obstacle? Where are all those points? So again, this is the obstacle in the environment. What is this black curve? It is the set of all robot configurations in which the robot exactly touches the obstacle. Okay? So if we go a little bit inside of this area, what are we guaranteed that will happen? Collision, right? So all the points that lie in this curve are forbidden configurations, meaning that those are configurations that represent positions of the robot in which it collides with the obstacles. Okay? And what is the free space? Everything that lies outside of this black region. Okay? So now we describe the configuration space and the free space. And the nice thing about this representation is that we can now talk about motion planning and essentially ignore the structure of the robot itself and instead talk about the configuration space of the robot. Okay? This gives us a unifying way to talk about motion planning. Okay? So we usually, when we try to solve motion planning problems, we won't work in the workspace of the problem where the robot lives, but in the actual configuration space of the problem. Okay? Great. So now we know that the motion planning problem that we have, this is another illustration, breaks into regions that are free or forbidden. We want to find a collision-free path for our robot. This translates to what problem in this space? We saw its discrete analogy in the discrete graph case. Now we are given an initial configuration and a target configuration. And what do we need to find? What do we need to find for our original motion planning problem? A collision-free path for the robot, right? What is the analogy for that in the configuration space perspective? A collision-free path for a robot induces what special type of curve in the configuration space? What do we know about this curve? It is continuous first of all, right? Because the robot can jump around, can move, can teleport from one configuration to another. What else do we know about this curve? Where does it live? Entirely in the free space. Okay? So now instead of thinking about trying to find a path for the robot that doesn't collide with obstacles. We just need to think about finding a continuous curve that lies entirely in the free space of the problem. Okay? So this is exactly the same problem that we had earlier in the discrete graph, only in the continuous setting. Okay? But usually those continuous structures are much harder to reason with than discrete graphs, but we will see how to overcome this in a few more slides. Any questions? Okay. So what we will do now, basically, is given already the free space of the problem, we will see how to transform this representation of the free space. In this example, how do we represent the free space? It's a polygon again, okay? Given an initial goal in the free region and a target goal in the free region, we need to find some mathematically rigorous method in order to uncover the continuous free path that we have here, okay? We will now basically cast it into a discrete problem on a graph. Okay? So the first thing we can do in the setting, so let me emphasize that this example is specifically for the two-dimensional case. We have, let's say, a point robot that moves amid obstacles. These are the obstacles. Or conversely, we have a two-dimensional robot that induces this free and forbidden space of the problem. Okay? Given some representation of the free space, which is a polygon, we can decompose it into a collection of trapezoids, as in this example. Okay, so we have here several trapezoids. This is one, this is another one. What is the nice property that those trapezoids have? They are all convex. Okay? Each of those objects is convex, which means what? That as long as the robot moves from one point in the trapezoid to another point in the trapezoid, we are guaranteed to have a straight line path that is entirely in the trapezoid itself, which means that this path is free as well. Right? Okay. So now that we decompose those trapezoids, the free space into trapezoids, we can also tell which trapezoids are neighbors to which other trapezoids. For instance, this is a trapezoid that is neighbor to this trapezoid. Okay? And all those trapezoids induce a discrete graph that is similar to the graph that we had earlier. Okay? Again, we can represent each of those trapezoids as a vertex in the graph. We will connect two trapezoids that share a common edge by an edge. Okay? And again, we translated the continuous problem that we had of computing a continuous curve taking us from here to which problem? Finding a sequence of vertices in our graph. Okay, again, this is a graph induced by those trapezoids here. Questions? Yeah?
Are we putting a vertex at the region between two?
So the reason why we add it here, yes, so first of all, we do put a vertex that represents, let's say, the center of the trapezoid. And the reason that we put a vertex on the edges because it's not clear exactly how you would move from this trapezoid to this trapezoid because there are many options how to do that. So here we decided we will just pick the center of the edge between those two trapezoids. Okay? Great. So we discretize the problem. We are given now a start configuration and a goal configuration. How do we find a continuous path between them? what is the first thing that we do? Those configurations are just coordinates. Our graph, the graph that we constructed, is a graph of trapezoids. So how do we bridge this gap? What do we need to do? We need to identify for each of those configurations what is the trapezoid that contains them, right? Now that we've done that, we search for a path on the trapezoid's graph. Okay? How do we transform this trapezoid graph path into a continuous path? Okay, so we ran let's say the A-star algorithm on the trapezoid graph, and it retrieved us this sequence of trapezoids. The only thing that we need to do now is to tell how to connect every let's say, center of a trapezoid with the center of the edge that it connects to. And what do we know about those trapezoids? They are convex. Because they are convex, each one of those edges is collision-free. So given a discrete solution on the graph, we can now transform it into a continuous path for our continuous problem. Okay? Yeah?
Is there a way to solve this problem without discretization? Obviously, that's how you bring the problem down. But, is there a way to do that?
There are different methods that you can use. You can, for instance, walk on the boundary of the free space, of the polygon of the free space, until you will reach a point that you can, from which you can see the goal point. But then again, you're still doing some discretization. Although this structure is continuous, we're representing it in a discrete way, because the way we would represent it is simply by a sequence of vertices and the edges that connect those vertices. Okay? It's just that this structure represents a continuous structure. Okay? Yeah?
So here our goal is not to find the shortest path,
Right.
but actually any path.
Yeah, yeah. So for now, we're just looking for a path, and we will, in a few more slides, we'll see how to find the shortest path. Again, let me emphasize that this is for a very simple case of a robot that has a two-dimensional configuration space. Okay? So just to make sure that the details are clear, those algorithms that, for instance, compute this trapezoidal decomposition are quite complex eventually. But just to give you an intuition how one would compute such a decomposition, we do the following thing. We are picking a vertex of the forbidden region. A vertex that is found on the boundary of the forbidden region. And we draw a ray that goes up and down from this specific vertex until what happens? Until it reaches another edge that represents the forbidden region. How would we implement this in practice? This is the boundary of the forbidden region is represented by a polygon. A polygon is simply a sequence of lines. Okay? So what we will do here, we will find the intersection of this ray with all the different edges of the forbidden region. And we will pick which ones. We will pick the intersection points that are closest to this vertex. Okay? This will induce one trapezoid, or two trapezoids in this case. Okay? This is how we would proceed. So all those continuous problems break down into a sequence of discrete decisions that we need to make. Okay. So this was about trapezoidal decomposition, and as one of you already noted, this technique only guarantees finding a solution, okay? Because we pick, in some sense, an arbitrary point in each of those trapezoids, which doesn't guarantee us to find an optimal solution. And it turns out that you can't actually fix the trapezoidal decomposition such that it will guarantee an optimal solution. We will need to use a different approach for that. Okay, so the approach that I would like to mention to you is called the visibility graph. Okay, the visibility graph is actually even simpler than the trapezoidal decomposition itself. So here again we have an illustration of the configuration space of the problem. Forbidden regions, this is a forbidden region as well. What do we do here? We try to draw an edge between every two vertices that are found on the boundary of the forbidden region. Okay? What is the motivation behind that? What happens, let's say that I want to find a shortest path that goes from this point to this point. What is guaranteed to happen eventually? The shortest path, would the shortest path reside always in the white region? Yeah, what was the comment there?
You're going to be hugging corners.
Yes, if I want to find the shortest path, guaranteed shortest path, then eventually I will need to be very, very close to the obstacles, okay? Meaning that eventually, so think about a robot that comes from here to here, the shortest path will look something like that. It will try to reach this point in the shortest manner possible. From here to here, the shortest path is again from one vertex to another. So the shortest path maintains the shortest distance from every pair of vertices at any given time, okay? So this is the motivation for the visibility graph. Again, how do we describe this graph? We try to draw an edge between every two vertices such that the edge doesn't hit any other obstacle in the environment, okay? So for instance, an edge between this vertex and this vertex doesn't exist because the edge would go through this forbidden region. Okay, but this is an edge that we add to the graph. So our graph in this case consists of all those black edges that we added here. Okay? So this is a pre-processing step that we do before we are even given the query, which is the start and the goal configuration. What would be our next step given those queries? This is a graph that is based only upon the location of the forbidden regions in the problem. Okay, but we still need to connect to this graph in some way the goal and the start vertices. How would we do that? We'll do something similar to what we did before. We will take our start vertex and try to connect it to any other vertex in the forbidden region as we did when constructing this graph. Okay? This will guarantee a graph that contains both the edges of the visibility graph and edges connecting to the initial and the goal vertices. Okay? What is the next step? Find the shortest path over the discrete graph. Okay? Any questions? So, of course, I'm omitting here a lot of details. Those algorithms are eventually quite complex to implement because there are a lot of special cases that we need to treat. But I hope that you get at least a taste of how those algorithms would work. So one aspect of those algorithms that we ignored so far is what? Here we assumed that someone already gives us the free space, the representation of the free space of the environment. But this is not really realistic, right? Because what are the initial inputs that we are given? we're given some representation of the robot and representation of the obstacles in the environment, which are strictly different from the free space of the environment. Okay? How would we compute the free space of the environment? So we already had one example where we took our disk robot and we had one triangular obstacle. So we took our disk robot and just drew it around the obstacle in the locations in which the robot exactly touches the obstacle. Okay? So we can do this in general. Let me show you an illustration. Here we have this example. We have a triangular robot that is only allowed to translate. We have here two obstacles, and we actually have another obstacle, which is the boundary of the environment. How would we compute the free space for this problem? Let's just look at one specific combination of obstacle and robot. We will slide our robot such that it exactly touches the obstacles, and all those points that lie inside of this area are the forbidden configurations. Okay? Again, is it clear how it works? We're just taking our robot and we're sliding it along the obstacle such that either a vertex of the robot or an edge of the robot touches the obstacle. Okay? So the induced purple and gray region introduce a forbidden space region for our problem. Okay? We do this step for every obstacle independently. Okay? This induces two forbidden regions. And we also have to do the same thing for the boundary of the problem. So once again, we take the boundary of the problem and we take our robot and draw it around until we touch all the points on the obstacle. So this induces the free space of the problem, which is represented by the white regions in this part and this part. Okay? And this operation that we did here has actually a name. It's a very common operator that is used in mathematics, which is called a Minkowski sum. Okay? A Minkowski sum is basically taking the sum of all the points from the original set and the second set. All the points that lie in this area are in the Minkowski sum. So how would we use the Minkowski sum in our case? Here we will have a representation of the robot, the polygon of the robot, and the polygon of the obstacle of the environment. Okay? And I won't go into the details about how to compute all those regions. Let me just mention, yeah. And I don't really expect anyone to go into the book and see how it works there. I just want to mention that there is actually an implementation in C++ called Seagull Library, Computational Geometry Library, where all those algorithms, including the trapezoidal decomposition, visibility graph are already implemented, so you won't have to do this problem, won't have to do this thing. Okay. So any questions so far about combinatorial algorithms for planning in two-dimensional configuration space? Okay, great. So what we ignored so far, most of our problems don't induce a two-dimensional configuration space, right? Even if we'll take this triangle and allow it to translate, its configuration space is already three-dimensional. Okay? So the question is whether we can extend those techniques that we've seen so far for the two-dimensional case to higher dimensions. So let me just show you a visualization of how it looks like. Ooh. All right. Sorry. So here we have a nice visualization for a specific robot. This is the green triangle here. The difference from all the examples that I showed you so far is that we also allow this triangle to rotate in addition to translate. So the configuration space of this problem is already three-dimensional, right? Okay. Let me just jump back. Okay. So here we can see that whenever we rotate the robot, we move up or down on the z-axis, and while we're doing translations, we're moving on the x or the y plane. So we can think about this three-dimensional setting of the problem as basically taking all the layers of the two-dimensional spaces in which the robot is only allowed to translate and gluing them all together. Okay? So again, as the robot is only allowed to translate, we just move on the z-axis. Yeah, I can introduce more complex motions. Yeah, here you can see that it moves simultaneously, translates and rotates. So this induces those paths. Okay. Now I want to show you an example with obstacles. Yeah. Here already for one obstacle, or even an interaction of the robot translating with this edge around this vertex, this induces already a quite complex terrain in 3 dimensions. And if we glue all of those together, we get this 3-dimensional shape. Okay? So we're not actually going to work on this geometric structure, don't be worried. We just want to get some intuition how this space looks like. Okay, so once again, the easiest observation to make here is that if we take a specific angle of rotation, we already know how to compute the free space for this specific problem, because here the robot is only allowed to translate. So this way we can compute all the layers and glue them all together. Okay. So this is basically the illustration that we have here. For the example that we had earlier, we know that for a specific angle of rotation, we can compute one layer. Okay? And we can do that for all the angles of rotation of the robot and glue all those layers together to obtain this 3-dimensional shape. And what does this 3-dimensional shape represent? The gray area is again the forbidden region. The white area is the free space. And we once again have the same problem. We are given an initial configuration and a goal configuration, and our goal is to find a collision-free path that lies entirely in the free space of the problem. Okay? So how we proceed from this? There are extensions of the trapezoidal decomposition we have seen earlier. They are much more complex. Yeah. They are quite complex. Before wrapping this section up, I just want to mention that it seems very, very hard to work with those geometric combinatorial algorithms. It is indeed quite hard. The benefit of those algorithms is that if you already know how to construct such an algorithm, you have very strong theoretical guarantees about the way this algorithm works, in the sense that those algorithms usually guarantee to find a solution if one exists, or to report that none exists otherwise, which is not something that the grid-based methods know how to do. In many cases, those combinatorial algorithms have guaranteed complexity bounds, meaning how many steps of the algorithm you need to run until you are guaranteed to find a solution if one exists. Okay? In many situations, you can also uncover the optimal solution for the problem with those combinatorial algorithms. The disadvantage of those combinatorial planners is that they are inherently limited to problems that involve a small number of degrees of freedom. And this is actually unavoidable because we can show mathematically that most of the motion planning problems are actually computationally intractable, meaning that those problems are hard to compute, they are p-space hard, np hard, etc. And we can guarantee, we can even find specific examples of those problems which would require for every algorithm to execute an exponential number of steps. Okay? So in some sense, this is unavoidable, this combinatorial explosion. Another aspect that is quite challenging when working with those combinatorial algorithms, that each algorithm is basically described for a specific type of robot or a specific problem, okay? And they usually do not extend from one problem to another. For instance, if we have an algorithm that is that treats the case where our robot is translating it in the plane, an algorithm that would solve a similar problem in which the robot is also rotating in the plane would require a slightly different algorithm already. Another disadvantage of those approaches is that they are usually quite difficult to implement in practice. Because they reason about geometric data structures, they often require software that can deal with infinite precision, which is quite hard to work with. Although, as I mentioned earlier, there is the Seagull library, which has very useful implementations of all those algorithms that I mentioned so far. Yeah.
Can you go to the slide where you ran the triangle?
Sure.
Yeah. So here you are saying that we shouldn't enter the purple region, right?
We get the purple region from the way we move this robot around. How exactly?
Without rotating.
Without rotating, just translating. So this is a two-dimensional problem again. This is just for the case where a robot is translating. You can see that it doesn't change its orientation from one configuration to the next.
So now what is the implication of this purple region? We should not enter it.
We should not enter it. This is the forbidden region of the problem. The motivation for that was that both in the trapezoidal decomposition algorithm and the visibility graph algorithm, we already assumed that someone already gives us the representation of the free space of the environment. But we actually need to compute this representation on our own. So this is how you compute it. We are given here just the obstacle in the workspace of the environment, a representation of the robot, and from that we can infer the forbidden region that is induced by this specific obstacle in the configuration space.
But if we are given a target position on the top left, I mean, even if we are entering it, we can actually achieve it optimally, right? But why are we like being, I feel we are being too safe by shading of this.
Oh, so the thing is that you don't actually know how it would look like in advance. This is what we do right now. We are studying, learning how this white region looks like. What is the shape of the free space of the problem? This is what we are trying to compute. Of course, for us, it's very easy to see that a robot can move from here to here because it won't hit this corner of the obstacle. But the computer doesn't know that. We need to explain the computer how to work we actually have to prescribe every step that the algorithm should make in order to compute this region. Okay? So again, about this example, just to clarify, we initially get this representation of the problem. This is the workspace. Those are the obstacles in the workspace, a start configuration and a target configuration. The next step will be to compute the free space of the environment by computing the forbidden region for each of the obstacles independently. And how do we do that? By the illustration that I just showed you, computing those purple regions. Then we overlay the purple regions together. But here again, we ignored one obstacle that is already in the environment, which is the boundary of the workspace. Okay? So we do the same thing with the boundary of the obstacle of the workspace, which limits us to this rectangular region, which is then overlaid with the forbidden regions that we computed earlier. And this induces this free configuration space, which is the white region here and this white portion here. So back to your example, here, for instance, we can no longer reach this region because of the obstacle that is in the boundary that we had in the environment.
So X8 and X7 are only representative of the centroid of our robot?
Yeah.
Oh, yeah. Then it's
This is the configuration of the robot. Mm-hmm. Any more questions? Okay. So just to wrap up, we started with graph-based approaches, which discretize our continuous problem into a discrete graph by losing some resolution of the problem, which means that those techniques are usually not complete. Okay? They are not guaranteed to find a solution if one exists. But using combinatorial algorithms that actually compute the representation of the exact free space of the problem, then those techniques can discretize the space into a discrete problem without losing information, and by that guaranteeing either completeness or optimality. We saw the cell decomposition method, as well as the visibility graph, which also guarantees optimality. But we alluded to the fact that those techniques are quite hard to work with in practice. And the reason for that is that if you want to have strong mathematical guarantees on your solution, you must work very, very hard. Because the space in which our problems are represented or described, the configuration space, can be very complex. Okay? And what we will see in the next lesson is how modern motion planning algorithms attack those problems. It is not by explicitly constructing the exact representation of the problem, but by densely sampling the problem, and by that constructing some approximation of the free space of the environment. So those algorithms are quite strong in practice, and we will see a lot of them in the next lesson, as well as their theoretical guarantees. Okay, so I will see you in a few days.